Hi guys. These notes are for 4.1b. Sorry I can't be there with you today, so hopefully you'll be able to understand the screencast for today's notes. So we're going to do more practice on the extreme value theorem. So for the first example in your note packet, it says find the extreme values of, and they give you a piecewise function here. So it's always a good idea to kind of have a picture in your head of what this piecewise function looks like before you start drawing it. So to the left of x equal to 1, including the input of 1, I can tell here I have a upside down parabola because the x squared term is negative. And then to the right of x equal to 1, I have a line, slope of 1, y-intercept of 2. But that's irrelevant because the y-intercept isn't within this interval for x is greater than 1. All right, so what I want you to do right now, I want you to pause the screencast and attempt to draw this particular piecewise function. Okay, here's what you should get. All right, so it looks like this. We are asked to find the extreme values. So to find extreme values, you have to look for those critical points, and you also have to consider the endpoints. Now, since this function is continuous and is not bound, it's not on a closed interval, that means the extreme value theorem does not apply, and you do not have to evaluate the function, the original function at particular endpoints to see if they're absolute maximums or minimums. That also means you're not guaranteed an absolute maximum or an absolute minimum. All right, so what we're going to do right now is we're going to look for these critical points for extreme candidates. At this point, I can't call them global maximums and global minimums or absolute maximums or minimums because the EVT did not apply. I can tell by looking at the picture that I'm assuming this one's going to be a max and this one's going to be a min, since both sides of my function, one side's going down infinitely, and the other side's going up infinitely. There's no global max and global min. All right, so critical points. Critical points exist when for values of x that make when your derivative equals 0, and also when the derivative does not exist. So I can see right here that, see how I have the parabola that meets up with a line, and that creates that cuspy corner we talked about before. And so I know that the derivative does not exist right there. And I can tell right here that I have a horizontal tangent that's going to meet. So I'm kind of having an idea looking at the visual. All right, so here's what I'm going to do. I take the derivative of each of these functions here. So for the first function, 5 minus 2x squared, I take the derivative, and I get negative 4x equals a 0. So for what values of x is this derivative equal to 0? And that would be at 0. This one here, I just get that the derivative equals a 1. There's no x values in there. So this particular function doesn't tell me that there's any more critical points based on the derivative. Now, there is a critical point at x equal 1, and this just is a coincidence that these two numbers are the same because of the cuspy corner over here. So these are my two candidates for extrema. All right, so does EVT apply? We already talked about that. Does not apply because the function is not on a closed interval. So now I just need to do the final part, and that's find the extrema. So to find the actual, you have to find the locations, meaning inputs and outputs. I know my two inputs. I just need to find my outputs. So in this one, this was pretty easy. You could just take your inputs here and plug them into the function that it applies to. So since x is 0, that's a number that's less than or equal to 1. So we plug it in here, and we get an output of 5. So I can tell also by looking at the picture, that's a local maximum. So I could write it as an ordered pair, 0, 5, or I could use function notation and write f of 0 equals 5. The other critical point is x equal to 1. So technically, I do need to plug it into the top one because this says x equal to 1. So if I plug 1 into this function, I get 5 minus 2. So my output then is a 3. So the local minimum is f of 1 equals a 3. All right, example number 2 has a typo in your packet. It says that the h of x function leads with a negative, but we can't use that one. You end up getting imaginary roots, and so that one doesn't work out well. So we need to make that 2 a positive 2. All right, now I know that this is a polynomial function. It's a cubic. The leading coefficient is positive, so it's gonna look like a curvy lightning bolt where it's coming from the bottom and then heading up as you're going from left to right. Now, does EVT apply? And that's a no, because h of x is not on a closed interval. All right, so what I'm going to do first, I'm going to find these critical points. So I found the derivative. You can check here. I had to do a lot of whiteout, so that's how I figured out this was wrong with the negative in front. All right, so 3 times 2, 6x squared. 2 times 3 halves is the 3, and then becomes x. The derivative of negative 9x is a negative 9, and then the negative 4 becomes a 0. So now I need to basically find the value of x that would make this equation equal a 0. I'm going to factor out a 3 to make the trinomial factoring easier. Oh, that's not right. That's not right. No, it is right. Okay, so now I'm going to factor my trinomial here. This is a 2 right there. There we go. So 0 equals 3. So I'm going to put a 2x here, an x here, a 3 here, a 1 there, and this would become plus and minus. So I get 2 values of x. I have to set this function here, the 2x plus 3, equal to 0. Oops, 0. And x minus 1 equal to 0. So my critical points are negative 3 halves and a positive 1. So you can see that. All right, so now I actually have to determine which of these inputs make a maximum or a minimum. So I put the calculator, I put the function in my calculator. All right, so let's see. Zoom in there. Okay, so I put the function in my calculator, and then let's just see what happens when I hit zoom 6. All right, so I can see there's a local maximum here and a local minimum here. And this appears, this x value here appears that's where the negative 3 halves is going to go. And the 1, the x equal to 1 right here, that's where the local minimum is going to go. So I'm just going to make a little sketch over here in my graph. Oops, wrong way. Okay. So let's see. All right, so it doesn't really matter. Let's see, something like this. Something like this, and it goes down there, and then up again. All right, so I'm looking for that point and that point. So I can then go to my table, and I'm going to type in negative 3 halves. And here's my output. So here's negative 3 halves, comma, 6.125. And that's my local max. If you want to go and find out what that is, if it's a fraction, feel free. And then at x equal to 1, right here at x equal to 1, my output is negative 9.5, and that's my local min. Done.